So hi everyone, and thank you for coming to this colloquium. So today we're very happy to welcome Roya Mohayaee from IAP. So Roya has done her studies in Great Britain and the UK, and then she did a postdoc in Nice, then again in the UK, until she joined IAP. So she has worked on quantum field theory and then on cosmology and gravitation. And today she's going to talk about testing the cosmological principle. So welcome.
Thank you. Thanks very much, Sonia. Thanks, Sonia and Ken, for organizing this. It's a pleasure to be back here. I haven't been back to APC for years. So yes, as Sonia said, I also worked on quantum field theory, but today I'm not going to tell you about quantum field theory. So sit back and relax. It's on something much, much simpler. It's about testing the cosmological principle, as you see. So it's a work that I've been doing for the last 15 years with these collaborators that you see. So these are probably many of you know. And Mohamed Remy, Jacques Collin, Nathan Seacrest from US, and Sebastian von Husek. So what is cosmological principle? As you know, it's the hypothesis that the universe is homogeneous and isotropic. And basically in physics language, what it means is that no matter which direction you look, universe looks the same. No matter where you are, it looks the same. But what does it mean quantitatively? Basically, it means that the metric that you write is invariant on the translation and on the rotation. And the most general metric that you can write in expanding universe, you all know, is Friedmann-Lemaitre-Robertson metric. It satisfies the condition of homogeneity and isotropy. But the universe doesn't have to be both. It can be, for example, homogeneous, but not isotropic. And in that case, you will have a preferred axis. Example of such universe are the Bianchi universes, Bianchi metrics. It could be inverse, that is, so these are Bianchi matrices. It could be inverse, that is, it could be inhomogeneous but isotropic. That's much easier to imagine. In that case, you will have a preferred center. An example of this is Lemaitre-Tolman-Bond universes. And then it can be much more complicated. It can be neither homogeneous nor isotropic. And then you'll have a very complicated metric. You see here. An example of a universe like that, a model like that, is decorous models. So you see immediately the simplest reason for which we have chosen FLRW metric. The simplest reason is just because it is actually quite simple as compared to other metrics. In fact, when Einstein wrote his equations, the Einstein equation around 1915, many people, including Einstein himself, were looking for a solution to this equation. But of course, like most physicists and mathematicians, the first thing you want to do is to find the simplest solution. So at that time, Einstein didn't think that the universe was expanding. So he proposed the very first model to solve Einstein equation was the Einstein model. So Einstein model is a model in which you have got matter and you have got cosmological constant, basically counterbalance the expansion of the universe, and is symmetric and isotropic. Then came de Sitter, it made it even simpler, it removed the matter. So you have only got the cosmological constant in the Sitter model. Then, of course, later on, as you know, we had Friedmann-Lemaitre. Friedmann was really the first person, visionary person, who actually predicted in some sense, not predicted, but he wrote a metric for expanding universe. He said, well, I have this Einstein equation, I want to solve it. It can expand, it can be open. There is a singularity at the beginning. If you actually also put Big Bang in there, and then it can have a crunch, we can have a closed universe, open universe. And then later on, Robertson and Bocke, who basically were not even physicists. They were mathematicians. They wanted to show what is the most general solution for expanding and homogeneous and isotropic. And they showed that Friedmann and Lemaitre metric is actually the most general solution for this special requirement to Einstein equation. Then the story continued. So then Einstein came back with de Sitter. Now we knew that the universe was expanding. So then they produced Einstein de Sitter model in which they had matter, but they had no cosmological constant, because now Hubble discovered it, actually, the expansion of the universe in 1929. So 7 years after Friedman and Lemaitre, which is amazing because Friedman and Lemaitre actually saw it in Einstein equation, but Hubble discovered it in 1929 at the beginning of 30s. And then Einstein and de Sitter, they came back and they said, okay, the universe is expanding, so we don't need cosmological constant. Now we have got matter, and then they wrote it for expanding universe. Now we know that Friedman, Lemaitre, Robertson, Volcametric at very early times goes to Einstein, de Sitter universe, and at very late time goes to de Sitter universe. This effort was really to just solve Einstein equation. There wasn't any real principle until it came Arthur Milne. Arthur Milne was the very first physicist who actually proposed the cosmological principle. He had produced a model of the universe in which he didn't have GR. He had Newtonian mechanics, and he had a special relativity, called it a kinetic model of universe. And perhaps the best phrase about Milne universe is given by Dirac. And so this is 1937. So Dirac actually writes about Milne universe in these ways. So he says, we now feel the need for some new assumption on which to build up a theory of cosmology. This need is partially satisfied by the assumptions which Milne calls the cosmological principle. Milne was really the very first person who talked about cosmological principle. That apart from local irregularities, the universe is everywhere uniform and has spherical symmetry in 3 dimensions. Then he goes on later on in that paper. These assumptions are fairly plausible and have a great simplifying effect on the subject. And until there is more definite evidence of their inadequacy, it doesn't seem worthwhile to try more complicated schemes. So you see immediately that cosmological principle was really a way of understanding universe, understandably. And it became a very big subject of philosophical debate at that time. And one of the most important and influential person who did a lot for philosophy of science attacks this work of Milne, and he says the cosmological principle are fear dogmas that should not have been proposed. And this is by Karl Popper, who believed in falsifiability of science. But we are not in 30s anymore, and actually we do believe that the theories that we write should be falsifiable. We usually try, even when we write the most abstract theories, we usually try to go and see whether the observations agree with that, whether they can show them right or wrong in the experiments. We are sending satellites into space, so we don't have to believe in cosmological principle. We can actually go and test it by observations or experiments, if you like. So what is the most compellable evidence for cosmological principle? And the most satisfying evidence for cosmological principle is the cosmic microwave background radiation, which is isotropic to 1 part in 10 to the minus 5. These are very tiny primordial fluctuations in temperature of microwave background, and they seem quite isotropic no matter which direction you look. We attribute these primordial fluctuations to some quantum fluctuations at very early universe, inflationary models and things. They have been proposed to explain it. But this map of the universe at very early time has been obtained by cleaning a fluctuation that is 100 times larger, and that is the CMB dipole. Now, in order to see the CMB primordial fluctuation, you need to remove this one. This is 100 times larger, and it's attributed to our motion. It's not considered to be primordial. It's not due to some sort of primordial quantum fluctuation. It's attributed to the velocity of the observer. We, as observers in the sun, if you are in the heliocentric frame, we have a motion with respect to that CMB background, that primordial fluctuation, and that is what gives rise to this Doppler effect. This is basically a Doppler effect. That is what this thing is. When they found it, there were many other proposals, one by David, who's sitting here, that this could be of more fundamental origins. But mostly people believe that this is just a kinematic. This is not fundamental. But is it true? So what is the origin of this CMB dipole? So we think it's due to our kinematic, due to our motion, and it's the Doppler effect. In fact, for the very first time, even before it was really observed, it was detected by Dennis Sharma the very first time. And Dennis Sharma said, well, okay, now there is this. So this is after Penzias and Wilson discovery of CMB. He said, well, okay, there is this CMB radiation that has been discovered. Now, if we have got a motion, and we know that we have got a motion, then it should give rise to a dipole. And how did he find about our motion? He actually looked at the data, the velocity data that he had. And I will show you what sort of data he was looking. And then later on, about a year later, it was Jim Peebles and Wilkinson who actually calculated it, made a proper calculation without looking at the data, that CMB itself is a black body radiation, and we as observers are moving in a black body radiation. So this is our velocity, the velocity of the observer. And then in that temperature map, there should be a dipole. This is a dipolar effect. You see cosine of theta. And you can measure, by measuring this dipole of the CMB, the temperature dipole, you can find the velocity of the observer from just this simple image. Now, where is our velocity coming from? So you might say, but we said, cosmological principle said that the universe is homogeneous and isotropic. If the universe is homogeneous and isotropic, we shouldn't have any velocity. But cosmological principle is saying universe is homogeneous and isotropic on large scale. Locally, we know that the universe is not isotropic at all. And that we have very firm observations for it. If I look at the very local universe around me, here we are sitting, right, Milky Way, right in the center. And we know that, you see, there is a huge super AMA, a super cluster next to us, the Virgo cluster. Virgo cluster is a huge collection of galaxies. And we know that we are all moving towards Virgo. There is a Virgo-centric info that people have been talking about for 30 years. And this observation of these velocities, we know the whole of this region is falling towards Virgo. And this is actually what Dennis Sharma used to predict, in some sense, the CMB dipole. He said, well, okay, I have this velocity field nearby. I know we are all going towards Virgo. So if there is a CMB background, then when I look at it, because I'm not an observer at rest, I should see a dipole. But is that enough? Is Virgo responsible for the CMB dipole? Well, at the beginning, they thought it was, but very soon, you see Sandage and Taman, they came and said, well, no, Virgo is not. The pull of Virgo is not enough. We have to go further away. We have to go to Hydra and Centaurus. This is now, is the great attractor, to be able to actually explain the CMB dipole. This became a subject of huge debate. You see, this is what Taman and Sandage were saying. They were saying that Virgo is not enough. If you go and look further away, you see the great attractor. The great attractor is basically the supercluster of Hydra and Centaurus. And we are all having this Virgo-centric info, but us together with Virgo, we are all moving towards the great attractor. And they were claiming that this region, the whole mass and isotropic distributed in this region, is responsible for our velocity that gives rise to the CMB dipole. You see, the local universe is very anisotropic. Here we have got superclusters, here we have got warm. And, but this didn't last long. This lasted maybe for 3 years. And then there was this other work that people came 3 years later, that it became known as the work of 7 samurai. And they actually showed that, well, if you take the Virgo and great attractor and look at their velocity field, you see that it cannot explain the CMB dipole. You have to go even far away because the great attractor is around 42, 45 megaparsec. So they are saying that you have to go beyond 50 megaparsec. So it's been a subject of dispute. How far do I have to go to explain the CMB dipole? So this is one of the very first work that I did together with Subi and postdocs. So we decided to look at the supernova data because there was so much dispute. And we said, okay, let's look at it ourselves. And why did we use supernovae? Because the supernovae data are quite interesting. Not only they give us the angular position of the sources in the sky, but they also give us the radial distance or redshift. Not only that, they also give us the distances. That is, they give us also the peculiar velocities, that is, the deviation from the Hubble flow. And that makes them very, very interesting. So we took this bunch of supernovae for which we had the measured velocity, and we tried to see what is the velocity of these larger and larger volume around us. And you see, this is the very first bunch of objects at redshift of below 0.01. This is this variable cluster. And I'm showing you the, and then I go further away, and I've got Hydra and Centaurus. And this is the velocity that they create. This is the velocity of that volume, about 200 kilometers per second. And then I go away, and I add more structure, because now we can go away. We have more and more observations. So we know that there is a snow great flow, there is the huge point here, there is the coma cluster. And then we see the velocity. So this is the velocity of that volume. And then I do the same exercise for a large volume. Now I add Hercule. The direction is very close to the direction of CMB dipole. And then I go all the way to Shapley concentration, which is at around 150 megaparsec. And then you see that this is what the velocity I have. And then I go even further. And this is the prediction from FLRW metric plus first order perturbation on that, basically lambda CDM. So it sort of agrees with assumption of homogeneity and isotropy at 2Z, 1 to 0. But I only have about 1,000 sources. So the error bars are huge. And so it would be nice to have more sources. It would be nice to have a lot more sources. But if I go and look at the catalogs that give me a lot more sources, then I lose information, because measuring distances is very hard and it's basically local. So I have catalogs that are redshift catalogs. They give me the angular position of the sources in the sky, theta and phi, and they give me the radial position, the redshift, but then I don't have any distance measurements. But many methods have been developed to basically find the distances or the velocities, because the distance is basically related to the peculiar velocity. That is peculiar. By peculiar velocity, I mean deviation from the Hubble flow due to inhomogeneity, due to anisotropy. And so one of the methods is to look at the fluid equation, solve them in the linear regime. I have developed with some of my colleagues a method that is, I will just touch on it because this is yet another seminar. How do we get, basically the question is, how do I get, this is positions basically, you can consider them as positions. Now you want to find velocities from the knowledge of positions. It just sounds like magic, you know the position of these objects. How are you going to find their velocities? It's not possible. Well, it's possible, and methods have been developed. And I just touched at one of the methods that I myself have developed with some of the colleagues, and that is a method that is based on optimal transport. So the question of finding the velocities of these galaxies from just simple knowledge of their positions is the same question that was posed by Gaspard Monge, one of the most prominent French mathematicians just before the French Revolution. So Gaspard Monge wanted to know how to transfer mass from Dipole to Hamblin. He didn't want to just amuse himself. This was really for the military reasons, because Gaspard Monge was very close to the king and then later on to the Napoleon. So for the military reason, he wanted to know how to transfer mass from Dipole for the fortifications to Hamblin. By minimizing the cost of the transport. And this question is the same question as how do I go from the present position of the galaxies to the initial homogeneous distribution by minimizing some sort of a cost. And that we can solve. We have very mathematicians and computer scientists have developed very powerful tools to solve this problem. So this is basically a problem of optimal transport. You have the positions of the galaxies or the sources now. You know that initially they were distributed homogeneously. You solve a mixed boundary value problem conserving mass. This gives you a fully nonlinear equation that is Monge-Ampère equation. If you look at this equation, it's very similar to Poisson equation. It's nonlinear because you have got a determinant of a Hessian instead of a Laplacian. So you solve it and you find basically the correspondence and you find the velocity. So basically, just take my word for it, it's a fascinating scheme used extensively in various areas of science. And basically you put the positions inside this optimal transport machine and it gives you the velocity. And using those velocities, I can do the same exercise as I did with supernova. And here is the velocity that I constructed using my optimal transport machine. And you see, this is, you're sitting right at the center, going towards Vega, going towards Great Attractor. And now I can look far away, Shapley, which is a huge supercluster of 10 to the power of 17 solar mass. And they're all going towards Shapley. But it's not enough to explain the CMB dipole. And here you see that. So yeah, these are basically, this is the CMB dipole. This is where we want to reach. This is the prediction from lambda CDM. And this is what the data is saying after I pass them through optimal transport. And you see, it's not conclusive when I go here. The error bars are large, the data is not complete. And so it's not clear what happens. And this is the 2 sigma lines from lambda CDM. So you see within 1, 2 sigma, the data maybe agree, maybe do not agree with lambda CDM. This is a subject of, as I showed you, this has been, from the beginning, has been a subject of dispute, you know, between different people. And it still is, because this is a plot from a survey which is called 60F survey. So they measure also the velocities using various things like Fisher and fundamental planes. And so these are various other people who have done this. This is us, you know, using like optimal transport. These are other groups that have done it. And you see, this is relatively local. It's about 100 megaparsec up to Shapley, basically Shapley is here. And this is basically 60F. So you see, there's a huge discrepancy between different people. And now very recently, this is 2016, very recently, about a few weeks ago, there was this new data that came out from Brent Collier from their 6 cosmic flow 4, and they are here. So you see, there's a lot of things. So then you see, I myself got very tired of this because, you know, somebody said, well, we've reached, we haven't reached. So what would be nice is to go and look here. You see, if you could look here, if I could look here, you know, and then there would be no dispute. If I found something, then it would be significant. So it would be nice if we could have gone really far. So this is just local. We could have gone really, really far to see what happens to the universe. Then I'm basically near the CMB, because that is what the cosmological principle is saying. It's saying that the rest frame of distant sources is the same as the rest frame of the CMB. So I should look at the distant sources. But what are the distant sources? Well, when I look at very far, I can't basically look at anything because in optical, I have nothing. But there are powerful sources, and those are radio sources and quasars. And we have got information on those. We have got surveys that cover quasars and radio sources. And these are at huge distances. These are at gigaparsecs. These are at redshifts of bigger than 1. Would it not be nice to use them, these sources, to test the cosmological principle? Now, there is a problem. And the problem is that when you go very far, you have got these radio and quasar sources. And you have got many of them. But then you lose information. You see, then we went to supernovae, to the redshift surveys. We lost information on distances of peculiar velocities. When we go from redshift surveys to imaging surveys, which cover very far redshift, we only have the angular position of the sources. We only have the theta and phi to consider spherical coordinates. So what am I going to do with just these 2 angular positions? How am I going to verify if the universe is isotropic or isotropic and homogeneous, or just isotropic, if I only have the angular position? I don't even know where these galaxies are. I don't have their distances. I don't even have their redshift. I don't even have the redshift to use the optimal transport machine to find the distances. What can we do with just these 2 coordinates? It seems that we can do a lot of things with these 2 coordinates. And this is a very old story in astronomy. It goes back to the work of James Bradley. James Bradley was in 18th century. At that time, many people, many astronomers especially, were looking at ways of falsifying or proving the Copernican principle, that is, there is a heliocentric universe and the Earth is moving around the sun. So they were saying, okay, if the Earth is moving around the sun, then when I look at the distant stars or the stars, nearby stars, there should be a parallax. The parallax is nothing but, you just look at your finger, you close one eye, you see your finger in one position, you close the other eye, you see your finger in another position, because the two eyes are in two different positions. So if the Earth is moving around the sun, the astronomers are saying, then when I look at a star, fixed star in June, it should be different, this position. And when I look at it, let's say in January, and I'm in a different position. And that was parallax. They were looking to measure the parallax. And there were many claims. For example, there was a claim by a famous astronomer, the Hooker. Hooker claimed that he had actually measured the parallax. Until Bradley actually put himself with one of his astronomer friends, and they tried to measure parallax of a star that was convenient. I think it was Alpha Draconis star, which was in good position. So they wanted to do it. And you see, this is the data that they got. And Bradley realized that actually, it seems like the position of the star doesn't depend on the position of the observer. It doesn't matter if we are looking at the fixed star in June or in July. It seems like the position of that star depends on the velocity of the observer. So in trying to find parallax, he actually discovered aberration. So aberration is due to the motion of the observer. If an observer is at rest, it sees the position of a star in a place. And if the observer has a motion, the position of the star will move. It's like, when we move and it's raining, so we have to just tilt our umbrella. And it's the same when you have a telescope that is on a stationary place or on a moving Earth. You have to tilt it. And that is the aberration effect. He made a discovery of aberration effect, and he actually he showed that the speed of light is finite, which wasn't clear at that time in 18th century. And he made the most precise measurement of the speed of light. So that shows, when you dig very deep, you can make discoveries. And this is aberration due to Bradley. So you see there is a observer's velocity. So you see if there is a rest frame, there's a star position is there. And if the observer is moving, the star position moves by an angle. And you see the aberration angle is related to the velocity of the position, to the angle between the source and the direction of the velocity observer. Not only there is aberration, no, this is aberration if you're looking at a fixed star. You might say, but what has it got to do with cosmology? I'm not looking at a star, I'm looking at distant universe. But it happens that I can use this method to look at distant universe. That is, now when I look at distant universe, I don't have just one source, I have a bunch of sources. And if I am moving towards a certain direction, then if in the direction of my motion, I see more sources than behind me and elsewhere. So I can collectively, if I count the number of sources, I see more in front of me than behind me. And that was due to the work of Ellis and Baldwin. Basically, Ellis and Baldwin extended the aberration that was discovered 200 years earlier, 300 years earlier, to cosmology, basically. And not only there is aberration, because when we look at sources using a telescope, usually these telescopes are flux limited. So there are certain sources that I would not see because they fall below my flux limit. But because I'm moving towards a certain direction, they would be Doppler boosted in the direction. So there is a second effect, which is known as Doppler boost. And using these two effects, I can find the velocity of the observer with respect to distant sources, very distant sources. Now, this is a very powerful method. And the reason why this is very powerful is because it's independent of the distance to the source. So no matter where your source is, how far it is from you, from the aberration angle, you can find your motion. So it's independent of the source. And it is indeed very, very powerful. So this is what they wrote, actually. So thus the existence of such an observed anisotropy is a test of the isotropy of the source count in the rest frame. The great power of this test, this is the Ellis and Baldwin aberration test, aberration and Doppler boosting test. The great power of this test is is that the measurement can be made and the result must hold for any source counts, whether in a wide or a narrow solid angle, for flat or steep source spectra, etc., irrespective of selection effects or source evolution, as long as the forward and backward measurements are done in the identical manner. So it makes it extremely powerful. It's independent of how you observe, it's dependent of your selection effect, it's dependent of the distance. As long as you are, when you're observing the sky around you, you're not selecting one direction above another. And so this is the test we used. And now we're happy because we could really look at the distant universe to establish or falsify cosmological principle. So the first sources that we looked were radio sources, as I told you, because these are very far, they're very powerful sources, so you can see them very far. We used the NVSS catalog, which contained about a few million sources, but we had to clean, we had to clean the galactic plane, so the sources below certain blocks, above certain blocks. And at the end of the day, we ended up with about 500,000 sources. And now, because it was above 40 degrees, so then we hashed it up with another catalog, which was SUMSS, which observed the southern sky. Hashed them together, we had the full sky catalog. And this is the dipole that you see. Basically, the blues are the directions that contain more than the mean, and the red are the directions that contain less galaxies than the mean. Now, the whole thing of establishing cosmological principle is the number count. It's actually quite simple. So you just look at different directions inside the solid angle, and you count. And you see, this is I do a number count in hemispheres pointed at different directions, and you see that I see a dipole pattern. This is not a fit actually at all to the data. This is just the data coming out, and it's fit by the focus. So there is a dipole in the number count of the radio sources, and you see the velocity that it corresponds to. So this is the velocity. So this is the direction of the CMB dipole. This is the direction of the dipole of the radio sources. The direction is very similar to the CMB dipole direction, but the velocity is more than twice as large. So the directions agree, but the amplitude of the dipole is larger. And this has been confirmed by different groups. Now, what is the significance of this result? We have only 500,000, is a ground-based, there are systematics. So this has a low significance. This is of significance of about 2.6, less than 3 sigma. So the next thing we wanted to do was to have more significance. So because less than 3 sigma, it could just be a statistical fluctuation. You could just find these dipole from just a statistical fluctuation. It didn't have to have anything physical significance to it. So how do we increase the statistical significance? So we sort of looking at completely different data set, and we were very lucky. Note that these data are from telescopes on the ground. So next came, we were very lucky that we had this Y-Saver here. So it's a telescope that scanned the full sky. It scanned about 700 million objects. All of them, of course, are not sources that are of interest to us. So we have to clean them up. It observed in 4 bands. And you see, these are the distribution, finally, of the sources that are of interest to us. These are quasars at very high redshift, and we have about 1,400,000 of them. And if we just now smooth this distribution of these quasars, you see these are quasars, and this is from a space telescope, so it doesn't have the systematics of a ground-based telescope. If we just smooth it, just by a tiny angle, then you see immediately that the dipole comes out, and the magnitude of this dipole is about twice as large as the CMB dipole. The direction is about 20 degrees from the direction of the CMB dipole. But what is the significance of this result? Could it just be a fluke, just a statistical fluctuation? Well, to establish first I tell you that these sources are mostly at high redshift. To find a redshift, the cross-correlated is EBOS, this EBOS data in a band that was very deep. And we also used data from the dark energy setting. And so this shows that most of the sources, about more than 98% are above redshift of 0.1, and mostly they are above redshift of 1. So there is not a problem of local sources. These are very distant sources, as is required to test the cosmological principle. And so in order to establish the statistical significance, what we have done some sort of a Monte Carlo. Basically, we have produced 10 million random sky. They mimic our catalog, the cat-wise catalog. They have the same mass, use the same estimator. We took flux randomly from the distribution of flux, and the flux index from the distribution of these alpha, the flux index. And then from these flux distribution and the catalog, every time we checked our null hypothesis. That is, we put an observer that was moving with the velocity given by the CMB dipole, that is about 367 kilometers per second. And then we saw if it produced the same dipole that we observed in the quasars. And out of 10 million random sky, only 5 produce the same dipole. So it cannot be a statistical fluctuation. The result is not a fluke. And if you translate this p-value to significance, then you get about 4.9 sigma. So this is the distribution of those 10 to the 7, those 10 million simulations. And you see where they are. This is the CMB dipole. And this is the cat-wise dipole. You see, this is far away. This is about 4.9 sigma. Now here we looked at only those that had a direction that were basically between the cat-wise direction and the CMB dipole. Now, does it agree with what I did earlier, the radio sources? Note that this data is independent from the radio sources. This is infrared. Those were radio sources. This is space-based. That was ground-based. Do they agree with the radio sources? So in a work that followed up the quasar work, we went back to the radio data. We only looked at the NBSS. This is NBSS data. We didn't patch it up with SQMSS to avoid generating systematics. This is our WISE data. And we looked at the NBSS again. And this is the joint significance test. So this is the NBSS. So here we were very, very conservative. We actually took anything that was in any direction, basically, because previously we restricted to an angle between the quasar dipole direction and the CMB direction. Here we just produced a 2D map. Basically, one is the dipole amplitude, and one is the angle offset from the CMB, and the other are 1 sigma and 2 sigma lines. And this is where our dipole is. So it's for the NBSS, it's about 2.6 sigma. And for the WISE, being very conservative, it goes to about 4.4 sigma. And once you combine them, you can get about 5.1 sigma. Well, combining them, one has to be careful, but once properly combined, you get 5.1 sigma. So I hope I've convinced you that these are two independent data sets. They are very few sources that are shared by the two catalogs, only 1 to 4%. And so there's no shared scanning pattern. So when you have got WISE, it's a satellite, it has certain scanning pattern that goes around ecliptic pole. Whereas the NBSS is not that. They don't have any shared instrumental design, no shared foreground systematics, because one is a space, one is ground-based, and minimum shared sources I've shown you is about 1 to 4% at most. And they are giving the same results. Now, we made all our data and the codes and the analysis, and the results, it's open access, so anyone can access them. Actually, now this is like 2022. Various other groups actually confirmed it, used the data. They use different methods, spherical harmonic fitting, etc., and using Bayesian analysis, they confirmed the results. Now I've reached at the end, so I'm not going to go back and conclude because it's quite long. So let me just finish with 2 things, one from George Ellis and Baldwin. So what is happening here now? where do we go from here? Now, I've shown you that, the CMB rest frame doesn't seem to coincide with the rest frame of distant sources. Basically, the CMB dipole is not the same as the dipole of the distant sources. The dipole of the distant sources seem to be in the same direction, but of an amplitude much higher, more than twice as high. So they are saying, so what happens if there is such a disagreement? Then what George Ellis and Baldwin are saying is that if the standards of rest determined by the microwave background radiation and the number counts were to be in serious disagreement, one would have to abandon either the idea that the radio sources are at cosmological distances. No, we cannot abandon that because we know radio sources are at cosmological distances. Because at that time, they were not sure. They were saying, okay, maybe these radio sources are local. B, the interpretation of the cosmic microwave background microwave radiation as relic radiation from the Big Bang. So you want to abandon that? I don't think anyone wants to abandon that because now we believe that this comes from the Big Bang or something like that. And the third is the standard FLRW universe model we have to abandon. One of these three we have to abandon according to Ellis and Baldwin. And then I finished by reading a paragraph or two from a very recent review by Jim Peoples, Anomalies in Physical Cosmology, which was published in 2022. So Jim Peoples says, it's basically the founder of cosmology. He says, the lambda CDM cosmology passes demanding tests that establish it as a good approximation to reality. The theory is incomplete, of course, and open issues are being examined in active research programs. I fully agree with that, and I think most people do, because lambda CDM has been extremely successful. I mean, the full range of data that are explained by lambda CDM is amazing. It's not from the scale of galaxies to scale of, CMB, early universe, late universe. Many things have been explained by lambda. But there are open questions. So then he continues and he says, the dipole anisotropy in the distribution of objects at distances comparable to the Hubble length is about in the direction expected from the kinematic effect if the dipole anisotropy in the CMB is due to our motion relative to the rest frame defined by the mean mass distribution. But the dipole amplitude is at least twice the prediction. The anomaly is about as well established as the Hubble tension, yet the literature on the kinematic effect is much smaller than the 344 papers. Now it's about more than 1,000 with the phrase Hubble tension in the abstract. So then it just goes on the same practice. It's quite well established. Well, I leave you with that and let you find a solution to this anomaly. Thank you.
Okay, thank you very much, Roya, for this very nice and clear talk. Are there questions? Those from the audience? Yes.
Yeah, I have a question. So can you go back to the plot of the quasars that's in smooth? Yes, I know. Okay. Yeah, sure. Yeah. So when you do your simulations of the quasar dipole, you are you including any of the kind of like foreground effects that are kind of apparent here?
It's the same mass.
Right. So there's.
Could you repeat the question for people?
Yes. So the question is that when we are running our simulations to establish the significance of this result, whether we are taking into account the foreground effects, and I think by foreground effects you mean the galactic cut and the masks. Yes, sure. We have basically we are making a mock catalog of the WISE data, and we put the same mask, the same flux cut, the same galactic plane cut. So it's basically mimicking the real data.
Well, but there's not just a pure dipole here.
You have to wrap it up. You mean you're talking about higher multiples?
Yeah.
Yeah. So it's hard to establish. So when we looked at here, we just aim at looking at dipole. Now, when you look at higher multiple, it's very, we can't establish it. We need much more data. It's not enough to say that there are high multiples. Now, there are other people after us who came and tried to fit a harmonic analysis to this, a spherical harmonic analysis. And they found that actually all the higher multiples, apart from dipoles, are quite small in good agreement with lambda CDM, apart from dipole. And that is a paper that came after us by Adinoser and Tivari. So we didn't find any evidence. And anyway, we are not looking at higher multiples. We are not fitting, we are not doing a spherical harmonic analysis.
Yes, Martina,
yeah. In your slide from George Ellis, I guess 1984, he gave us the number of no, it was where there were the three options.
Oh yeah, sure.
And the first two seem rather non-palatable, but how would you change the standard FRW universe model to make it fit the data, either than just by hand putting in the bucket, you know?
I was hoping you will tell me about that. I was hoping you would tell me how to change the LRW. I mean,
it's really hard.
Yeah.
Are there any ideas?
Yeah. Changing a LRW, I don't know. But so what we looked at, now people have been looking at other things like Bianchi model and trying to fit the dipole and things. Tilted model, tilted universe of, Mike Turner. So in which you have got super horizon iso-curvature mode, because that was proposed initially by Jim Gunn and then worked out by Mike Turner. And so you have got iso-curvature modes that are not ruled out by CMB, and they are super horizon. Then they can give you a matter dipole, which is not the same as radiation dipole. And because there is a relative velocity between these two, the matter dipole and CMB dipole, that's why when we measure CMB dipole, we see about 300, whereas when we measure matter dipole, we see about 700. Now, there's a real problem is that the iso-curvature mode has to be aligned with the CMB dipole. So it's not clear, how you would align it. What is the mechanism to make these super horizon modes aligned?
Yeah, it seems like they're so close.
Yeah, it's fine tuning. So I don't think that is satisfactory. I don't think you can explain it with any sort of adiabatic mode, because then you would generate not only large motion at our position, but at the position of nearby galaxies. And there we have good measurement of velocity. So that is well constrained. Now, what are the other theoretical possibilities? Well, you tell me. It's for you.
I think next colloquium we need a theory talk.
Yeah.
With all the possible models. Other questions?
On the idea of alignment there, you have the two catalogs, the smooth dipoles of the two catalogs in one of your. And just to be blunt, they don't look the same, right? I mean, those don't look the same.
Yes, because so they don't look the same. I mean, the dipoles more or less, but because this is about 500,000 sources, this is almost a full sky. This has got 40-degree cut down. And then you put it in these coordinates, you see it like that. Because it's MDSS, so it's basically seeing the northern sky. Yeah, this is a full sky. Yeah, you're quite.
They look different.
Well, the directions are not exactly aligned, but they are not very far of each other. Now, what is interesting about these two catalogs is that they agree. Basically, they both show that it's a very high amplitude. The directions are about 20, 40 degrees from CMB dipole. But when you remove the kinematic dipole from both of them, the agreement between both the amplitude and the direction increases. And that basically means that there is a component of the dipole that could be fundamental. See? Yeah, because when you remove the kinematic dipole, the remaining dipole between the two agree even more.
If you're looking for, you don't have to have perfect alignment.
No, it's not a
perfect. Be within 20 or 40 degrees.
Yeah.
Right?
Yeah, but it still is the same in the same quadrant, right? It's not opposite.
Yeah.
Yeah. Yeah, we don't have a perfect line. Actually, when we go and look at the nearby objects to figure out what our velocity is, so these nearby objects that are basically pulling up, they are not perfectly aligned, but they are more or less in the same, and it's about 20 degrees. So you see Hadron Centaurus, Shapley, Virgo, they're about 20, 30 degrees from the CMB dipole, but they are more or less, but then there are fluctuations, right? You are not, it's not just one object.
Assuming that these statistics are driven by sources that are right above the detection threshold, like you must have more fainter objects than right above. Or is that taken care of?
Yeah, we have taken care of flux cut. So in some sense, we shouldn't have that actually. That we have.
And then my follow-on question was, I guess, is there any way lensing would affect it?
Yeah, so that's a very interesting thing. So we didn't do that, but someone, Murray from is he here now? Maybe he was here. Yeah. So yeah, he's probably come here because he was in Strasbourg when he wrote that paper. So he looked at the lensing effect, and apparently he didn't find. Yeah. But one thing would be nice to do is to do CMB lensing to see, but the signal must be tiny, tiny, tiny.
Yeah, it's not very true.
Yeah. But whether you could see, yeah, it's not going to change the dipole, but if you could see in CMB lensing, whether there are structures, at large redshifts, that would explain this dipole. Because one thing could be that we see nearby. This is one of the solution proposed by Jim Peoples is that when nearby, we know that you see many of these big superclusters like Virgo and so on, they're on a plane. Basically, they're on the plane of the supercluster. What if, when you look at very large redshift, those quasars and so on are also on a plane? And then that might explain, you see, the dipole that you see.
But
so
that is violating the cosmological.
Exactly. It's violating, but then it's explaining what is happening. Yeah, I think at any rate, this basically violating the larger scalar subtotal.
Etienne.
Thank you very much for this very interesting talk, especially for our specialists. I was wondering first, so you say the amplitude is larger. That would be translated in, we would deduce a velocity which is twice larger. But how, so I have two questions. One is, well, second one. Wouldn't the amplitude depend on the luminosity distribution of your sources in the sense that if the luminosity distribution is very steep, then moving a little bit further towards the sources would increase the number of sources much more than if it were flat? Or is it a wrong idea? I guess it is a wrong idea because you don't pay attention.
I suppose if it's so that these are parallel, you see, we can establish them. So the spectral index, you see, we have them in the Weiss catalog, we have them for every single source. So you see, it's more or less a parallel. And then the second index that we have, basically the number index, if you want, or what people call the magnification index, some people call it. You can establish it. You see, you can see how it changes, the number changes its flux cuts. And you see, it's pretty steep. And it's pretty much a parallel. You don't really see a flattening.
But the steeper it is, the higher the amplitude will be.
But that is taken into account when we use this formula, you see. Yes.
Okay.
So basically, you see, this is alpha and x that go into that.
So you correct for that, and you still have twice the velocity.
Exactly. Yeah.
Okay. So now the question is, how can you make sense of it? In the sense that, I mean, okay, you have to drop isotropy and homogeneity. Is there any proposal for a metric that would do that in the direction and multiply the velocity by 2? It seems to me completely
Yeah, I mean, it is. I mean, the local universe is not isotropic.
No, but all this is actually I don't even see what's the relation with isotropy of homogeneity, because you have the two effects, the dipole of the CMB and this aberration effect. It all come just from our velocity with respect to the global point, whatever. So this velocity is what it is. So it means that the race frame of the CMB and the race frame of the sources are different.
Yes.
And how would a change of metric produce that?
Well, that I don't know. So I've just been here. I've been telling you that there is evidence that it's not.
Yes.
It seems like a convincing evidence. But now it could be that, you know, I'm not saying it's 100%. It could be that there's some problem with the data. No, I don't know what it could be, because you see, if the two independent data are showing it, if there was just one data, I would say very simple. Now there are two independent data, and then there are other people producing it using completely independent methods, and it's showing it. And then you would say, well, maybe there are problems on the galactic plane, but you see, the CMB dipole is not really galactic plane; it's above it. So I don't know what sort of systematic could produce it. Now, if it's not, if it's real, then that's why I was very interested to give this talk. You have got theorists here, so it's for the theorists to find out, you see, what it could be, what sort of universes. I mean, when there was a dipole, David, you had a paper with Paczynski. I don't know if it was right, but then on the entropy, but that was somehow ruled out. Yeah, super. Yeah. So you have got a fine tuning. Yeah. So do you have any other idea? Yes. 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 Yes.
The effect that you see, the dipole that you see is not only due to all velocity, but this is due to another intrinsic effect of the CMB itself. So it means that you have a kind of very large scale perturbation on the CMB itself. So when you see the dipole, you have a combination of in the opposite direction and reduce the intrinsic dipole.
Does that suffer from the same alignment?
Yes.
Yeah.
Then most probably maybe not. To compute the probability. Sorry, but we will see a combination of both. Right? Yeah. And then you will see the dipole in the CMB pointing in some direction. It will be a combination of our motion plus the x vector. It could be that they don't have to be perfectly aligned, but when you see the near combination, which is roughly aligned to our velocity, because that's being dominant. So it cannot be a small effect. Yes, so it cannot be a small effect.
The intrinsic CMB dipole independent of our velocity would have to be the opposite, reduced by a factor of 2. Would have to be the same direction, but opposite.
Yes, so then it depends how you. Yes, how you define the.
It is an alignment.
No one has to be careful with introducing too much intrinsic CMB dipole, because you can, well, still some people are claiming that, no, let me take a step back. So you can get our velocity from a kinematic interpretation of the CMB dipole. It's just an interpretation. So one of the papers right at the beginning that it came out was written by David, and other people have written also saying that maybe not all of it is kinematic, part of it is fundamental. It's cosmological, it's fundamental. Now, it happens that if the observer has a motion, not only in the distant sources, but in the CMB primordial fluctuation itself, you will have an aberration. And by measuring that aberration effect, there you can deduce directly the velocity of the observer. It's not an interpretation anymore. But measuring the aberration effect on the CMB is a tiny, tiny effect. And I don't think, can you correct me if I'm wrong? I don't think they have done it yet. Yeah. Sorry.
You're asking if they've measured the aberration of the CMB.
Yeah,
Yes,
they have been claimed. So their very first one, a Puri move, was at a very low sigma.
The thing about the aberration, though, is that I think for an adiabatic universe, you get it purple. Like it's you could interpret it as an intrinsic or a boost, but if you kind of have to, if you have an isocurvature, my understanding is that the aberration there would be an aberration caused by isocurvature, but it would be it'll look a little bit different than the aberration caused by which you can still get an aberration.
Yeah, exactly. So it's not yes.
But the aberration and the modulation of the anisotropies matches the direction and amplitude of the CMB dipole. But that's if you go through the math, that's kind of a given. Like there's not
fishy.
nothing fishy in the fine judgment, but looking at the aberration modulation of the anisotropies isn't like a new measurement. I wouldn't call it a confirmation.
Not really.
Because if you go through the math, a dipole should cause like an intrinsic or a kinematic dipole should still cause these effects.
You're saying they're not the same.
They're not the same. Yeah. So
Yes. Suppose it was not intrinsic and it was just kinematic.
yeah, then they would.
Then the aberration would give us the velocity. Yes. But what measurement?
So if it's not intrinsic, then the dipole you measure is also just the velocity.
Yeah, but that's an interpretation. Whereas the aberration, apparently you can actually, with aberration, you can measure the velocity, right?
With aberration, you can also interpret it as
I
velocity,
see.
but you can also interpret it
I see.
differently if you want to.
I see. So, okay, with aberration also, it's not a direct measure of our velocity, you're saying.
Depends who you talk to, but I think you go through the math and you can find terms from isocurvature that look like aberration.
Okay, great. Because in that paper, Puri move, and then there's a paper a few years ago, it seemed like they were claiming that, they sort of measure the velocity, and it is, agrees.
I think that so this is very biased because Douglas is my supervisor, so my understanding of this is that if you boost the CMB, right, the monopole boosts into this big dipole that you see, and you can either interpret that as entirely due to kinematic motion, or you can interpret it as some combination of our motion and something that's intrinsic in the CMB, right? But for adiabatic universe, you wouldn't expect that dipole to be especially big. That's intrinsic to the CMB. If you add isocurvature, then you can maybe have a different size CMB dipole. And then if you go to higher order terms, then you get the modulation and aberration of the anisotropies, and those are like hotter in the forward direction or squished together against all that stuff, right? You measure that, but if you go through the math with an adiabatic universe, all of those things can only be caused by. They will look identical if they're caused by a boost, as if they were caused by a dipole that just existed in the universe. But also in the adiabatic universe, we should have an especially big intrinsic dipole. But I don't have the rhyme on, but basically I think if you have an isocurvature caused a dipole, if you go through the math carefully, you can find position-dependent terms that will mimic aberration, but there's no reason that those should be aligned, right? Like your aberration from isocurvature doesn't have to be aligned with your aberration from the boost. So that's my intent. So,
Good. That's good to know.
Sorry, I suggest that since there are no questions answered, maybe we take it to a discussion around the coffee, so that the people who like can participate to the discussion, and the people who would like to go can
Merci beaucoup de la question. Moi, il n'y avait pas de